There we go. 50% of the material you've been tested on already. That's going to be 50% of the test, and then the other 50% will be from the material you haven't been tested on yet. So kind of half and half. So just keep that in mind. I mean, I know that. Does someone have a question?
Yeah, do you mean like material from semester from like physics 1?
Oh, no. Well, I mean, we're still like technically testing you on physics 1 stuff, right? Like,
no, of course, but not like specifically, I don't know, like forces or like Newton's laws.
Like he might not ask you a direct question on that, but I promise you he's gonna test you on Newton laws.
Okay.
Because Newton laws is kind of, it's not because he's taken a step back all the way to physics 1. It's just that should still be something, I think you're all seeing it. Like physics is one of those things that, I mean, it takes a lot of time. I think that's what Dr. Ivana was trying to express to you as well in class when he was saying, like, when you're a physics major, or if you plan to do that as your profession, it's totally different than anything else. Like, for like if you're, for med school example, right, you can get your undergraduate and go right into med school, but you can't, like, for a physicist, you can't jump right over into like PhD because there's different levels of the classes. So you take like this undergraduate level of like mechanics, and then there's a graduate level, and then there's a PhD level, and that's where you really are supposed to by then have had a firm understanding. But please don't hold yourself to too high of a standard and say, man, I was supposed to know everything about Newton laws when I walked out of physics 1. No, we're still kind of like teaching them to you. I mean, there's not a lot of them, but we're still kind of teaching them to you. And so we're still going to be directly testing you on those types of things, just like with kinetic energy and stuff like that. Like, we're still testing you on that stuff, which is, we're not talking about, I guess the one thing you could say is now we're no longer talking about a brick going down a roof anymore. Now we're using Newton laws and saying, okay, let's apply it to electric field or something like that. But technically, the electric field parts actually should be easy. It's just this one equation, really, right, or 2 equations. But what makes those questions tricky is that we're saying, okay, you got to apply Newton laws and put this electric field in it, right? And then it gets kind of abstract, but it's still overall like Newton laws. So I want to be careful the way I answer that, I guess. But he will directly be asking you about, I mean, when we're asking you questions about like a particle and a constant electric field, like we're just asking you Newton law questions, right? Or even when we talk about like a particle and a magnetic field, those are just Newton law questions, right? It doesn't matter like what field the particle's in, you draw the force on it and you do your Newton laws, right? The same way that you would from last semester. So anyway, he tests on a lot of stuff, okay? He really, really does take a step all the way back. But in terms of like Newton laws and kinetic energy, we're always testing on that. I think this last bit of stuff I was saying isn't as Newtonian, and we're explaining to you now why we kind of aren't using Newtonian physics anymore. So it's a little bit different, but everything through electromagnetism is definitely Newtonian, the way we were talking about it. So you'll always be applying like general old Newton laws and stuff. But anyway, any questions? So we started the semester with electric fields and electric force and things like this, right? But what like, you know, they all essentially were associated with something. And what were all these things associated with? A specific type of what? And the variable's a Q. Yeah, charge. Exactly. Okay. So, you know, there's a lecture. This is how we started this semester, right? We eventually got to a point where we said, hey, you don't need that charge to have an electric field anymore, right? But here at the beginning, this very beginning of the semester, we were really focused on charge. One of the reasons why, and I think we talked about it, I didn't have plans to go into too deep of detail in it because I wanted to focus on some of the more challenging ideas. But you know, like when he's asking you to do the, you know, like you have two conducting spheres and you put them together and you want to see like how the charge is distributed. He's essentially, you know, trying to test you on this very important concept that we're trying to start with, which is, you know, essentially charge is always conserved. And that's like the fundamental idea. That's why when you like put two spheres together, and in this class, these are just these spheres will always be identical in size and things like this. It's just they'll only differ in charge. You know, the charge has to be conserved. So that's why you add all the charge up and split it in half, because the charge is conserved, always conserved. And it works the same way when you're, you know, trying to polarize something. You know, if you pull charge from one, you know, let's say something's completely neutral. And you have like this piece of metal that's just sitting there, it's completely neutral, and then you like bring some, I don't know. I'm not going to go talk about this too much because it's really simple, and I think everyone understands this idea. But you know, when I bring this negatively charged rod just even close to it, I don't have to touch anything, right? I just have to bring it close. You know, it separate it. What happens here? Who can tell me? When I bring this negatively charged rod closer to this metal, this is like a like sheet of a conducting sheet of metal. Yeah, how? Good polarization. Does the rod attract the positive charges? Are you sure? So in this case, like we're talking about this piece of metal, the charges that are moving around in here are protons and neutrons, right? Or protons and electrons. Why did I say neutrons? Sorry. It's just like the natural thing to say next. I think I put protons, but protons and electrons are the charges in here. Do protons move? So then what happens here? How's this thing polarized? Good. That's 100% correct when electrons move. There we go. Right, so it's going to push the, right, this thing's neutral, but you know, there's negative and positive charges over here before we bring the rod close, right? And then, you know, there's all, you know, there's equal charge everywhere, right? It has the same amount of charge over here, but completely opposite, because the net charge is zero, right? So I'm using a very general picture here, but right, the net charge of this plate was zero, so it still has to be equal to zero in terms of charge. Like this would cancel this one out, 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 this would cancel this out, right? But they're sitting like this, right? And so when I bring this rod closer, what does it do? Like, you're right, it pushes it. Now be even more split. You should be able to give me the full answer here. Just think for a second. You know this answer. because this is the stuff we have to talk about. Even though we didn't use these words when we were talking about this, you should now be using these words. You said it pushes on the electron. So I'm asking you, like, how does that happen? You know this. It's hopefully you're not making it harder than it is. Yeah. Good job. Electric force, right? We say it repels, but why? Because what do we know? Oh, I am a little frustrated with Canvas because there's a lot of different ways to write this equation, but I think you all are writing it like this. K can be written a different way, but I think this is what you all are doing. And so, yeah, this is what's going on, right? This also kind of tells you, like, you know, the positive, why the positive charges. I mean, you don't want to think that way. Protons don't move. Just let's say that. I shouldn't say what I was about to say. Okay, so what we want to do is we want to look at this equation, right? And how would this equation work as I brought, as I bring this closer? Like, what's going to happen in terms of this equation? Explain it to me in terms of this equation here. There's going to be a force that's repulsive, right? That's going to push on the negative charge. And there's going to be another force that's attracted by the positive charge, right? But in essence, it's that F. So all these go an F. That's fine. Right? Which means as you bring this rod closer, you know, these are going to move over here, and now the negative charges are going to outnumber the positive charges, and now there's not going to be any more negative charges over here. And so we have this polarized plate, right, where this is negative, oh my goodness, negatively charged on this side and positively charged, right? It's polarized now. Does that make sense? So yes, you're right, it repels, but you should now be saying, oh, this all happens because of electric force. Electric force causes repulsion and attraction. So when we say something polarizes, things are polarizing because of that force. Does that make sense? Okay. So that's what's super important to really understand. I mean, there's different types of ways to you know, charge essentially an object, but all those different charging methods have to do with some sort of polarization. So, you know, make sure you review those. Like I said, we don't have the time to review, you know, a month's worth of material in 3 hours, every little detail, right? So, you know, again, if you were to ask Dr. Mugana what's going to be on the test, he would say everything. I've heard those words come directly out of his mouth. Okay. I've heard when we were in class in person all the time, so you'd say, hey, Dr. Mugana, what's going to be on the final? Like, what should we focus on for the previous information? He would literally say everything. Okay. So he wants you to, you know, make sure that you have all these ideas in your head. But I mean, I would say, and I bet you he would say the same thing, is like, you know, look at the titles of the chapters though. Like, in essence, like, that's what we want you to understand. So if you need a, you know, if the chapter's force and field, you need to make sure you understand electric force and field and everything about it, essentially, is what he's trying to say when he says everything. but you can use his, since there's so much to actually know about this stuff, you want to use his lecture slides as a guide, because that's what he means by everything. He doesn't mean go on the internet and read a book. He means look at my lecture slides. I want you to know everything that's on my lecture slides. Okay, and that's essentially how the final's written. He really does, like I said, pull from a lot of places. Okay, so but this chapter is about electric force, right? And so that's really the thing that we need to focus on here. But just keep in mind, right? Polarization happens, right? First of all, the main idea that we were trying to get you to understand with all that charging stuff was that charge is always conserved. Things like this, okay? So like between two objects, like when we were putting the spheres together. And then we also showed you, in order to like fully charge an object, it has to have some sort of net charge in terms of positive or negative, extra negative charge or extra positive charge, in terms of being considered a charged object. So that's all we're trying to say. All right. But these forces, right? Again, we've talked about force, and just like the next chapter, we can kind of just talk about all this together, to be honest, but we want to separate them a little bit. Is that when we're talking about potential energy and potential, all these things are really just trying to talk about really electric field, right? Electric field is really the thing that, if you're trying to take something away, should be the overarching concept. And as you can see, we got to a point in this class where that's all we were talking about. I mean, think about light. It's just an electric field, right? And a magnetic field. So, we start with these ideas. Force essentially comes from that idea, right? You just can't have force, right? Even though as simple as we drew this picture here where we said, okay, force is between these, what's going on here. The only reason why that force is there is because there's some sort of electric field. There has to be. Okay, because that force is produced by the electric field interacting with some charge. Does that make sense? Like when the field's there, it has potential to do something. And when you put a charge in it, what does it do? It pushes on it. That's what it has the potential to do. And when it pushes on it, right? Or I'm so sorry, when you put that charge in the electric field, it gives that charge some potential energy, and it pushes, when it immediately releases that potential energy in the form of kinetic energy. It starts moving to the right or to the left, depending on what the charge is, right? So that's the big idea that we want to make sure that we understand, because it's entirely connected. It's not like force and electric field to this one chapter and that's separate. Then we have potential and potential energy. No, I just gave you the entire story in one sentence, because that's how it works. Okay, it's not like the separate thing, then this. Okay, so first of all, let's just start with this picture that you've all seen, but it's just really good because it tells us everything we got to know in terms of like concept about force, electric field, potential energy, in some sort of constant electric field. Okay, now keep that in mind. If the electric field isn't constant, some of these things aren't exactly true. And we'll talk about the other situation. Those are the things you want to know as well. But this one, as you've seen in class, that even though we've talked about changing electric fields, right, and stuff like this, it's not something that we haven't talked about. But a lot of the application, when we started using a lot of the application, it all had to do with some like constant electric field, right? Like a capacitor's two separated plates, right? That's a constant electric field. Well, until the charges go away, right? And the same thing for a battery, right? Like the charges are there, like in between the two charge plates of the battery, it's a constant electric field. So that was the one that we were more focused on. And that's why this picture is really good, because every time we talk about this constant electric field, you need to have this idea in your head, because this idea applies to circuits. It applies to really all three chapters that we're going to talk about today. Okay. So keep that in mind, but also keep in mind that, you know, there's another way to look at it. We'll talk about that here in 2 seconds. So, and I want you to help me a little bit here. Like, which way should I be drawing the electric field? Left or to the left or right? Good. Good. Now keep in mind, and again, I'm going to start. Oh, you're fine, Sheila. Don't worry. This is real casual here. I know. Don't worry. But it's nice to see you. It's nice to see all of you. Wish I could see you, but we can't be in person, unfortunately. We also have this thing that we got to kind of jump back and forth to. So let's talk about it because it's related to what we're saying. But if we don't know the answer to that question, then it starts with this, right? Like, what if I had just a positive charge? Like, let's say this positive and negative charge are nowhere near each other. If I had just this positive charge here, which way is the electric, like, which way is an electric field produced? What's the direction of the electric field that's produced because of a positive charge? That's really what I'm asking. These are the things he's really going to be asking you. And I know it's straightforward, but let's just make sure that we know. And that's an important thing. Why is it so? Why do any of you know? You should know this answer. Do you know why it's so important? Good job. Away from positive. Good job. Do you know why that's so important? Why is it so important to know this direction? Well, I mean, there's definitely a lot of answers there, Sheila. So I mean, you know, but there's a really fundamental idea. So you know, you're not, you know, saying good things. That's important to know for that reason, absolutely. But a little bit more fundamental. These should all be even. And anyway, I'm not a machine, and just trying to draw an example here. but electric fields are what? No, the electric field isn't a force. Think mathy, very mathematical, but it's important. You got to think this is a very important thing. Starts with a V. Yeah, it's a vector. You have to know its direction. And how does it get its direction? How does the vector direction? How do we get the vector direction for an electric field? That's your what being you're like, why are we getting this? Is it to solve problems or something? No, it's because electric field's a vector. You need to know the direction of it because it's just not a value. It's just not electric field's this. It's like, no, electric field is a value and a direction. Okay. This right here is not a uniform electric field. Good question. Okay, it's very important because he's going to ask you this question as well. That's why we're doing this on two different. He's going to ask you, you know, he wants you to know the difference between these two, and know that like what's going to happen in both situations. But I'm jumping over here just to make sure because there was a little hesitance answering the question when I asked which way the direction of the electric field should be here. So I just want to make sure that we know that direction. I probably should have just started here anyway. So this is the direction of the electric field for a positive charge. Why do we need to know it? Because it's a vector. We need to know its direction if we're going to study it or understand it or be able to talk about it or anything like that. We can't just talk about it like it's a value. And then negative charge direction? Good. So positive is outward, negative charge is inward. Good job. Just to make sure there's no confusion, do I need a positive charge to have this negative electric field? Like, is the only reason why this positive charge has an electric field here is because there's some this negative charge has an electric field because there's some positive charge hanging out here. Okay, good. That's its own electric field, right? Negative charges have their own electric field, and they have a vector direction as well, right? And their vector direction is inward. And that's essentially like, if you were to ask like a physicist, what's negative and positive charge, they would tell you it's something we had to make up. Like, we don't know if the universe thinks of, like protons and electrons in terms of positive and negative charge. But what we do know is the universe thinks of protons and electrons as opposites. They do two different things in an electric field, and they have their own electric field themselves, right? And they're completely opposites of each other. And so to understand that as humans, right, we said, what's the easiest way to think about that? Plus and minus. Those are complete opposites. And that's exactly how this even came about. Okay, so so this is electric field. How do we know it's not uniform? What yeah, for each, yes, so like for the positive charge, right, it's just not all pointing up, right? And really, if I were to draw this properly, these are three-dimensional, right? There's electric field coming out at us. These things almost look like the SARS virus, right, where it has the little protein just poking out everywhere, right, in all three dimensions, but it's the electric field in this case. So it's also pointed out as, but yes, in terms of this two-dimensional picture that I have drawn here, it's clear enough. They're not pointed in the same direction, right? Like if this one's pointed to the, up and to the right, and this one's pointed down to the left, those are clearly not the same direction, but they're coming from the same charge. Okay, so because they have different direction but coming from the same charge, we know that alone is our first one of our indications that we know that the electric field isn't constant for this specific charge, right? Where like over here, you all told me to draw the electric field like this. Well, this is same direction, same magnitude. Right? How do we know it's the same magnitude? How do we know this is like the electric field has the same, what is it about the picture that tells us, I mean, I'm not an artist, but it's as good as good that they're equal, for the best as I can do, they're equal distance from one another, right? Where over here, I mean, it's clear they're not, right? I mean, right here, they're a lot closer together than they are right here, right? They get further and further apart the further away you are from the charge. And that's true for negative charges. As you get closer, they're closer together. As it's further away, they're further apart, right? So that is literally, he wants you to be able to, right? Dr. Ngan is very conceptual. He wants you to be able to conceptually see that stuff. That's why he has you draw pictures all the time and stuff, because that's a very conceptual way to look. But good job, right? And we also know, right, there's a few equations for the electric field, but the one that'll really describe what we're trying to talk about right here, and this, I'm going to write it down here on the bottom near the negative charge, but this is true for both of them, right? Because we give you a lot of equations for electric field, right? And uh, uh, anyway, oh, I was looking at that. I was like, something doesn't look right. There we go. Okay. Um, uh, so that this is the one that really describes what we're talking about, and you can see that it works in terms of the inverse squared law, right? So we know that the further away you get, the smaller, right? The larger the R, the smaller the E. The smaller the R, the larger the E, right? That's a mathematical relationship in this equation, but that this equation is the one definitely telling us what's it's not uniform in terms of mathematics, which is something you should understand and know, right? That this is describing that specifically. Where this one over here, how do I write the electric? How's the? Do you remember? Do you remember what the electric field equation is for this? He gave it to you. You should know it. It's very important to know. So it comes from Gauss's law. Okay, we'll talk about this a little bit more. But remember, I'll say this, is that, we've given you, no, that's force, Levi. And good job. I mean, you're saying good things, but we're trying to just explain the electric field right now, and why am I so focused on electric fields? Like, I thought force was an important thing, right? But it's not, because you wouldn't have that force without the electric field, right? You know what? It was harder to see now or when we were in this chapter, but you can kind of see that the order is important, especially when we were talking about induction, right? Like there's a very important order, right? It's just not like all these things happen, right? It's like, no, and it has to happen like this, right? So you can't have force and then you get an electric field. That makes absolutely no sense whatsoever. That I don't even know how that would be possible. You have to have a field first. And essentially all these things, force, potential energy, they're really just trying to, I mean, I would say potential energy is more trying to relate to the charge, but force and potential, they're definitely trying to talk about the space, the 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 field. Okay, because that's really the thing we need to understand. And the reason why the potential is kind of why we bring up the potential. Yeah, that's another way. Yeah, that one also works here. But there's an even better one. And it's the one he wants you to know. I promise you. I swear. I think it was on the test. I said I can't. Anyway, it's relevant what my memory is doing. But I know he specifically wants you to know what this equation is for like between two charged plates, and that's one way to describe. So Sarah, she gave that equation that Sarah gave is great, and that's when we know the potential. That's when we know the potential. But if we're just trying to find, there it is. Good job. If we're just trying to find the potential or the electric field based off of charge, and maybe I should have said it like that, but I don't think Dr. Dumana ever said that, so I don't think that would have made things any clearer. Um, uh, 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 the best way to do it is Gauss's law. Gauss's law is amazing. It's amazing. So despite all those equations that we give you for electric field, Gauss's law is the way to do it. Okay, and this is true for both sides. This is for I mean, they're the same. They're the same. Same thing. So, but this is based off of charge. Okay. So we'll come back to, do you remember where that's coming from? We're going to talk about it here in a second, but do you remember where that's coming from? It is Gauss's law, but I guess what I'm saying is yeah, that's very true right there. Uh, but how do we, what's the, what, where do we derive? Yeah, you have to know how to derive this. Where do we derive this equation from? You need to know this. I know it may not have been something, because we don't like to use those words in class, like derive, but he showed you how to derive this. He wants you to be able, it came from it's a word that starts with an F and then an L. Yeah. And there's two of them, and these are just them equal to themselves, right? That's where this equation's coming from. We'll talk about it here in a second. Okay. But look at the difference in these equations, right? So we have this equation that's describing the individual charges, and then we have this equation that's describing the charges between two plates. Okay, in terms of electric field, right? And they're much more specific. Like, look at this. Like, we have a bunch. There's a lot of charges in these plates. I drew 4, but these are very tiny. There's a ton, right? It's way better to try to look at what, as Sheila put it, which is 100% correct, more of like a charge density type situation, looking at the area of the plate and the charge density that essentially can fit inside that plate. But do understand, there's an area in here for the plate, and there's an area in here for the thing that we call the Gaussian surface. But I don't know if Dr. Mbana got that far. Anyway, okay, so because this electric field isn't uniform, then what happens when I put a positive for the positive charge? If I put another positive charge in that electric field, what is it going to do? Good. And how is it going to do it? It's great to say repel, but always tell me why. Yeah, or Dr. Newman, I mean, not me. Yeah. 4, right? There's going to be an electric force on it, and when that electric force, I mean, the minute we put it in there, right? And remember, that's what's slightly different than a magnetic field. Remember, for a magnetic field, we have to, the charge has to be moving to get the magnetic force in a magnetic field, but not here. I can just put this positive charge near this other positive charge, and there's going to be an electric force on it, because that field's already there, right? If I take this thing away, the field's still there. Where's the force come from? It comes from when I put the charge in there, when the charge starts to interact with the field, right? And then there's this electric, immediately, right? Because the minute we put it in there, the charge is interacting with the field. Is this Fe, and then that's the equation that Levi gave us. Well, let me write this more appropriate. Again, I think you're using K, but it can be written. Just K has another way to write it. Sometimes we write it to epsilon, sometimes we don't. But I don't think he uses that anyway. So and force is also a vector as well, right? So these two things, don't forget that they need to have signs, and their signs are indicative of their direction, right? So I didn't give any like positive Y, positive X, anything here, so we can't really do that. I can do it. I guess we kind of need to do that, but and it's going to be harder to do for the electric field, but definitely for the force, if we say, the direction and it's moving is, negative y, then the force equation is going to be what? What's going to be the sign? Sorry, why did I say it like that? What's going to be the sign for the force equation? I think I was trying to get too many things out of my brain. Sorry there. What would be the sign for the force equation if that direction that it was moving was negative y? Or the direction the force is in. I shouldn't say necessarily moving, but the direction that the force is in. It'd be negative, right? Because force gets its sign from the direction that it's pointing, right? And that's what, I was saying earlier when I was saying, when it was asked, like, are we going to be tested on Newton laws? Well, yeah, right there, right? Even though that's electric force, like, you need to know that force is a vector. I mean, I guess that's not like directly a Newton law, but I mean, that's coming from physics 1. Maybe that's what I'm trying to say, is like that stuff that comes from physics 1, right? It's like, well, the direction that it doesn't matter what forces it is, electric force, magnetic force, the direction that it's pointing, if we've labeled that as, because we can label these any sign we want, but if we've labeled that as positive, then and that's the direction the force is pointing, then it's positive. If it's pointing, if we've labeled that direction as negative, then that's negative. Okay, so keep that in mind. Is this force constant? Good. And how do you know that? Good. And why is it diminished? Good job. Why is the force decreasing as it gets further away from the charge? So Levi's saying some good things. So why is that's close? But and based off what was said right there, why then is force decreasing as it moves away? Because what else is decreasing? There, the electric field. Yeah, you could say distance too. If you're like looking at this equation, you could say, oh, right here. You could say, oh, well, there's the same relationship, but you should be aware that, this right here is the electric field equation, right? Because we know, like, another way to write electric force is E times Q, right? So, and again, see, this is the stuff he's going to ask you, but this is all from physics 1. So Sarah asked, is acceleration also decreasing? You should be able to tell me that. You shouldn't. That's a question from physics. Like, he's going to ask you something like that on the test. Is that is acceleration going to increase or decrease? So conceptually, like, why should you, what do you know? This is a Newton law question. This is Newton laws right here that I'm asking you. You can give me an equation, but that's not what I'm looking for. Conceptually, how do you know that the acceleration is decreasing? You should, if you leave physics with anything in your, yes, Levi, good job. Force decreases, accelerate. Why? Because what's the saying that should be in your head? And I'm not joking. If you leave physics with anything, it needs to at least be this. Okay, you can't forget this. This wasn't like some side thing. It's like, oh, there's all this other important stuff. No, this thing that we're saying right now is the most important thing. It's Newton's second law, right? Net force is the what? Net force is the source of acceleration. Does net force exist without, does acceleration exist without net force there? Can I have acceleration but no net force? Why not? No. Good. You need force to have acceleration. You need net force. It's not just force, but net force, right? You need net force to have acceleration. That's the concept that should be in your head. You shouldn't think of acceleration as anything else. Net force comes, acceleration comes from net force. It doesn't even exist. And what mathematically is acceleration? Not in terms of an equation. Tell me conceptually, but it's a mathematical definition in words, not in equation. Acceleration is just the measure of the net force. The acceleration is just measuring what the net, sorry, not the measure of the net force, measure of what the net force is doing to the object. It's like, okay, the net force is affecting the object by how much? That's what the acceleration tells you. How much or how little, however you want to think about it, the net force is affecting that specific object. The net force can be an electric force, it could be a push, it could be anything. Does that make sense? That's what should be in your, if anything, if you leave physics with anything, it should be that. Okay? When there's no net force, there's no acceleration. Why? Because you can't measure something that isn't there. That's actually the best thing that should be in your head. Why isn't acceleration there? Because acceleration is just the measure of what the net force is doing to the object. If there's no net force, how can I have acceleration? You see? All right. So make sure that you understand that, okay? Because he's going to test you on that. He's going to test you on it in magnetic fields and magnetic force as well. He asks you about Newton laws. He wants you to understand what Newton laws are and what they're saying. So there we go. What's going to happen? So acceleration is not going to be constant as well, simply because we could write, it's getting a little crowded here. Simply because we could write because this, if this isn't constant, this isn't constant. They're proportional. Okay. So what about for a negative charge? What if I put a negative charge in the next to the big negative charge there? What's going to happen? Good. There's going to be a repulsion on it because there's going to be an electric force, right? Developed on it because the electric field. Good. Good job. And it would be directly opposite, right? And would that be constant? Because of everything we've already said, right? The force isn't constant because the electric field is constant. Well, but remember why? Why does the force diminish as it gets further away? Because the electric field diminishes. The force goes down by the exact same amount. It's the equation, right? The exact same amount as the electric field goes down, like the exact same amount. So because this Q is a constant, it's just there. So the force is really changing because the electric field's changing. You see that? And that's what's so important to know, is that the force has this relationship with the electric field. Okay. So what about here now? What about when everything's constant? Okay. And I do the same exact thing. First of all, everything's constant. So what do I mean by that? The electric field's constant. That's something you should be able to recognize. We already said why, I believe. So if the electric field's constant, just tell me what that means. I know that sounds like such a simple question, but it's something that we know is conceptually kind of difficult to understand. So we want to make sure. Okay, good. But what does it mean when the electric field's constant? That's all I'm asking. That's great. Good stuff right there, anyway. But what are we trying to say when we say the electric field's constant? Good. There we go. Constant direction, constant magnitude, right? Essentially, the electric field isn't changing. There's no the value of the electric field is the same as the value of the electric field right here is the same as the value of electric field here is the same as the value of electric field here. It's constant. The value doesn't change. That's what that means. Make sure you understand that. And then obviously, yes, it has to be direction as well. It can't be one or the other. That's why that was stated so well when we said magnitude and direction. Okay, you don't have it's not one or the other, it's both. Okay. Make sure you understand what that means. And that's why, because the electric field is constant, it's not changing anymore. It's not like this. It's the same value everywhere. That means that the force must be the same value everywhere. Does that make sense? It has to be. It has to be. All right. And again, there's a lot of different ways to write the electric force, but because you can write it a lot of different ways over here, I'll be honest with you. You know, there's this, and then there's the way we've already written it. But this one's a little bit more appropriate for this because the electric field is going to be constant, and then you just get that Q. And when you solve for this force, just like, you know, the electric field is the same right here, the same right here, the same right here. That also means that the force is the same right there. They're all the same. It's going to be the same value of force and direction of force everywhere. So this equation can be simplified like this, very simply, E times Q, because the E isn't changing. It's going to be one magnitude no matter where you're at in this electric field. And it's true over here too. I'm just using this one on the left, right? So it's much easier to just think of it this way because that's what's occurring. Right? But if you need to, you can totally also still, you know, maybe, you know, you weren't given the value of the but I'm telling you right now, if you can use this equation, you can use the bottom one because this right here is the electric field. But I'm gonna write Zoom and say, why did you change everything now of all times? At least wait till everyone's on break. Okay. Okay, so that's what we're saying. Okay, so keep that in mind. So this is also this electric force is also constant, and it also has has a direction. Like in the case of the positive charge, what is the direction? Oh my goodness. Which way is the direction of the electric force? Which way is the force direction? Yeah, to the right or to the left. We can say well, to the right it's positive x, and to the left it's negative x. Yeah, see, that's the best way to think about it, though. See, that's conceptually what uh, uh, Sarah just said is perfect. Okay, because that's what should be in your head. It should be that simple, nothing complicated. You should be able to just roll that off your tongue and think that way. For positive charge, it's the same direction as field. Because if we don't have, what if we don't have any charges there? We just give you an electric field and throw a charge in it. You should still be able to look at it and say, oh, the electric field is to the right. That means if it's a positive charge, the force is also going to be to the right. Or if the electric field is up, then that means that the force on a positive charge is going to be up. Right? Like automatically, like that's the best way to state it. Force is in the same direction as electric field. Okay. And what about for a negative charge? Good job. Force is in the opposite direction of field. So that's how we have to have that in our head, okay? Super important. Okay, and this picture essentially puts it all together for you, like all the information you have to have essentially memorized, right? And remember, this is for constant electric field. This is for, or what we should say, uniform electric field. This is a non-uniform electric field. Okay, so you should know the difference and know what's going to happen. He's totally going to give you a non-uniform field, put a charge in it, and ask you what the heck it's going to do, versus when you put it in here, because they don't do the same thing. And good. And then what do we know about now kind of moving to the next chapter? And again, we only have 3 hours here, right? Totally impossible to do everything, but there's going to be reviews in SI. So, if you want to talk about mathematics deeper or anything like that, we can, but it's really definitely for a review to solve problems. All of Dr. Dungana's review is pure problem solving, right? He just gives you those questions, but doesn't really go through concept. And so we're hoping that, him and I are a team. So, I do the concept side and he does that. But, because he also can't give you the review that he's going to give you on Monday isn't probably going to be a cumulative review. So keep that in mind. No, that one works. I'm not too sure what you're referring to there, Levi. But let's just kind of stick to we can't really get off, talk about oddball things like I was saying. Those little details, we could, trust me, we can get into 1,000 details I haven't talked about that are in your lecture slides. Okay, we don't have the time today. We only have 3 hours, so we gotta get the main overview. Okay. All right. So, and also keep in mind the other review, which is still posted. Remember, I did a review on all this stuff initially. Remember that the review I did for the first midterm? That's still posted on. I gave you that link, so you can go watch that, which is in way more detail. I believe. I'm not too sure. Anyway. So what about potential energy here for the positive charge? Is it going to be larger near the positive side or near the negative side? It's in the announcements. It's like 2 announcements down, something like that. So good. So the potential energy is going to be higher on the left side for the positive charge, and lower. And I could try to find it and send it out again later, but I'm just letting you know it's still there. Is all I'm trying to say. So right, so it's lower on the right side, higher on the left side. Okay, just very conceptual. And again, what you should know about this is when we come over here, pinch off. Is this any different? So for the positive charge, is the potential energy higher near the positive charge or further away from the positive charge? Good. So it's large there, right? We're like U out here somewhere would be what? Yeah. And this is all a fundamental property of the universe, right? Potential energy, right? It has to, it can't, if something's moving with kinetic energy, it's getting that from the potential energy. So the potential energy has to be going, right? It can't be constant, right? If something's moving, it doesn't matter the system. It's irrelevant if the electric field's constant or not, right? If it wasn't moving and had some potential energy and then begins to move, that potential energy is going to decrease because it's just converting over into the kinetic. The kinetic is going to be equal, right? They're going to, right? And then it's going to the kinetic energy is going to increase I had some picture in my brain but I wasn't saying things right, is going to increase as the potential energy decreases, right? And then as we bring, like for this, because this is a much nicer picture, right? So as it moves this way, it's gonna gain kinetic energy, larger kinetic energy. But if I were to take this positive charge and move it back to the right, then it's going to be gaining potential energy, right? All that uh, kinetic energy that it had moving right is essentially going to be converted back into the potential that it had over here, and then I'll let it go, and all that potential will go into the kinetic again, right? But the reason why we talk about potential energy, electric potential energy, more than kinetic energy in the potential energy chapter is because electric force is a conservative force. This is another very important thing from physics 1. Okay, and if you know you have it, there aren't many conservative forces out there. The way you know a force is conservative is because it's proportional in some way to displacement. Not every force is proportional to displacement. Like look at like friction isn't proportional to displacement, proportional to mu and n, where uh, elastic potential energy is related to the elastic force. It's directly related to what? Displacement. Right there. The x is in the equation, right? So that's what we mean. That if the displacement is actually in the equation directly associated with the force, that's going to be considered a conservative force. There's not many of them out there. Okay, but the electric force is one of them. Okay, it has r in it, right? The distance is in there, so it's proportional to that in some way. And because of that, it's totally conserved. It's considered all non-conservative. This is, I'm sorry, not non-conservative. This is what should be in your head from physics 1. All conservative forces, those are the forces that get their own potential energy. As you notice, there was only certain forces that had potential energy. Gravitational potential energy, elastic potential energy. That's all you learned about last semester. And then this semester, electric potential energy. Okay. You've never heard of tension potential energy, have you? Because it doesn't exist, because tension isn't technically considered a conservative force. It's not proportional to displacement. Okay. But the ones that because they're so special, the universe considers them so special, is what I should say. The universe gives them their own potential energy. So this conservative force gets a potential energy. Okay. It's where all this stuff's coming from physics 1, okay? All right. So for a negative charge, is the potential higher on the left or on the right? Good. So it's higher on the right. Go over here. And why does it go lower? Because it's not disappearing into thin air. It's just going into the kinetic. Right? The potential energy as it moves from right to left for the negative charge, the potential energy is just converting to the kinetic energy. And then what about potential for a positive charge? Is it higher or lowered on the left? So Levi said it's higher and lower for both of them on the left. Is that true? Good. Okay. Don't get into the craziness of potential. The reason why potential is kind of difficult to understand is because it's coming more from math than physics. But I hate to say that because, believe it or not, math has come a long way because of physics. Math wouldn't have done some things because of physics, but also vice versa. Is that we wouldn't have done a lot of things if math hadn't already done it for them as well. So math has this thing called potential. Potential isn't a physics thing. It's not like this is no, it's a math thing. And so because we bring it into physics, we kind of can describe it a few different ways because based off the math that it's giving us. Okay, it's not a science concept. It's more like based off the math it's giving us because the potential is very mathy, right? It's telling us something just very specific. Anyway, what am I trying to get to here? Is that you're going to see potential. You have seen potential discussed a lot of different ways. You've seen potential discussed as potential energy per charge. That's correct, right? One way to talk about potential is by potential energy per charge. You could say, yeah, the potential is equal to the potential energy per charge, right? And this is 100% correct. This is always true. But a lot of students get really, really confused because they're like, well, wait a minute. Based off this equation, well, let me say this first. A lot of students say, okay, this is cool. I get what you're saying about potential being equal to potential energy per charge. Okay, that makes sense. The only thing that throws me off is I know like potential energy, right? It needs two charges. So if potential is potential energy per charge, how come I can have potential without two charges? Because that's what this equation is saying, is I have potential without two charges. So we just don't want students getting confused. Some students have like said, they have been confused by this and hear one definition, hear another one, and think, oh, someone's saying something wrong here. It's like, no one's saying something wrong here. What we haven't really got into depths with, and we're not going to, is that this is a mathematical idea and we're explaining it a certain way. And to believe it or not, if we were in the calc-based physics, we would just tell you the potential is, when we divide potential energy by Q, we are trying to look at potential energy in terms of just the space. Space. We're trying to get rid of the charge associated with it. So when we divide potential energy by Q, this cancels out. It's no longer there. And then it becomes this equation, right? Which is no longer U, it's V. But when we do that mathematically, we're just trying to look at a property of space. See, we can get into all these details in here, but that's why it gets a little confusing. And that's why if you go watch the review that I gave you for this first chapter, I gave you these pictures of potential in terms of, being this gradient, because potential is the gradient of the electric field, literally, mathematically, because that's another way we can describe potential. We don't have to call it the potential energy per charge at all. We can just say it's the gradient of the electric field. It's like, why are you calling it two different things? Because we can. Mathematically, when we do the math, it tells us those two different things. So that's what it is. Okay, so don't be confused by it. Don't be confused that we call it a lot of different things. Just kind of understand where we're trying to come from here, where in terms of the potential, the whole reason, because what happens is for the next chapter that we're going to talk about here, which is circuits, that's the thing that we bring into circuits is potential. Out of all these things we talked about in these two chapters, electric field, electric force, potential, right? We bring in potential. Why? Because potential is potential a vector or a scalar? Yeah. But it can tell us something, because Sarah gave us a really good equation earlier. I was kind of waiting till now to write it. Right. Well, we've all seen it, but we can write the potential, but it's a change in potential. It's not just the potential, right? In terms of the electric field, because the potential is kind of a way to talk about the electric field, but in a scalar way. That's why when we divide by Q, we're essentially looking at the potential energy in terms of just the space. And what is the space? The space is the electric field. Okay. And so potential, again, this is change. Remember, just like the difference between change in kinetic energy and kinetic energy, there's a difference between change in potential and potential. Okay, keep that in mind. But this right here, right, we can see that there's a direct connection from potential to the electric field. And that's exactly what, if you want to know the reason where the heck potential came from and why we started talking about it in physics, that's the main reason why. We needed an easier way to talk about the electric field. Potential lets us do it in terms of a scalar value. Okay, so if you have anything, if you want to have something in your head for potential, have that. Okay, but it's really just this mathematical product that's helping us do a few things. And you should understand how it works. And we show you how it works. That's what this picture is. We're showing you that the potential is always highest near the positive charge and lowest near the negative charge. Why is that? That has to do with the gradient thing that's in the initial review that I sent out to you, that I'll send out again. But I explained that gradient thing in there. And that's where that's coming from. That gradient always works that way. It's always lower near the potential, always, near the negative, always higher. And it's actually indicative of the path the charges are going to take as well, but we don't have time to go there. Okay, so this is the overall idea. Now, also, do keep in mind, we said the electric field's constant, right? We said that the force is constant here, right? The electric force is constant, right? We said those things, correct? Electric force and electric field are constant in a constant uniform electric field, right? In this uniform electric field. But are potential and potential energy constant in a uniform electric field? No. See, these are the things, I know we never said it because we want you to go home and kind of think about these things. But now we're at the end of the semester, so I'm kind of telling you a few things, but those are the things you should notice. I don't know if we ever directly said that, we talked about it a little bit, but you should know that the potential and potential energy are changing in a uniform electric field. And they're also changing in a non-uniform electric field. Okay. When does the potential not change? When don't we have a change in potential? Essentially, I'm asking you, when can potential be constant? Asking where potential zero is different, and hopefully you understand that. So Levi said when there's no electric field. Anyone else wanna? Is that true? Is it? When is potential constant? I'm not saying zero. I'm saying when is potential constant? Not zero. Constant. Where potential zero and where it's constant, it's kind of two different things. What is that? Not kind of. Okay, so potential, sorry, I was just reading the chat. I have to go back and forth and they moved everything, so I can't read anything as fast as I can. Good. Okay, so it's what Levi said. It's when the electric, when there's no electric field. Okay. Yes, good job. There it is. Electrostatic equilibrium. That is exactly the application that we gave you, that Dr. Gonna want you to know, right? Where potential doesn't change. And why doesn't it change? Because there's no electric field. And that, remember we talked about, like, that's the connection you can make. You can say, okay, well then, so how do I know when I have an electric field? When there's a change in potential, because changes in potential are directly correlated with an electric field. Not potential though, see? And that's the thing, see, it's changes in potential that are connected to the electric field, not potential though. You can have potential and not have an electric field, but you can't have a change in potential without an electric field. You have to have an electric field to have a change in potential. So when is potential constant? When do you just have a potential? When there's no electric field. See, the electric field is going to cancel itself out here. I mean, this is vectorly drawn, right? I'm using the vectors to show you that they're going to cancel. But how would we do it mathematically? Remember, you'd use Gauss's law. You'd have to say, okay, let's say that like this way is positive y and this way is negative y. So for this particular electric field and this particular electric field, right? This one's pointing in the positive y. This one's pointing in the negative y. So that means, and let's call this E1 and E2. So that means it would be E1 minus E2. This is how you would, he wants you to be able to do this, but it is that simple, right? It's just as simple as adding or subtracting the electric fields. Here it would be zero. Why? Because you would use, you would use this in this specific situation where, oh my goodness, we're just saying two charges here, right? So we know it's gonna, the electric field for this charge we'd write like this, and the one for this one we'd write the same way. So when we put these in the equation, since it's right at the center, the R's are the same for both of these charges, right? Right directly in the center. That's kind of stopping me. Right? So we know that, and let's say these Q's are also the same. That has to do with electrostatic, right? These charges are equal. Then we know that this right here and this right here are going to be the same equation, but they're just subtracted from each other with the same numbers, same equation with the same numbers. So it's going to be equal to zero. So we know electric field here, or even if you did the math here, it'd be equal to zero. Or if you did the math here, it'd be equal to zero, because it would proportion out based off of R. But we don't get into those details in here. What he wants you to know, what he really focuses on is in the dead center. But it really could be anywhere in here. The electric field zero. Okay. But E is equal to zero. When E is equal to zero, V is constant. When is V zero? When is it zero? Remember, constant is like, it has a value, it has a number, it's just not changing. But when is it zero? That's why I don't like calling zero constant, because it confuses students, because they think zero, but constant is a non-changing number. Zero can be constant, but call zero zero and any other number that isn't changing constant. When is V zero? That's what I'm asking. It would be related to something like this, is the best way to probably explain it. So remember, literally V is negative over here, which means it's below zero because this is a scalar value, right? Good, 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 good. Somewhere in between here, right? You got to think that way. Like over here near the negative sign, it isn't zero. The potential is negative. It's below zero. And over here, because remember, potential's a scalar value. So those signs mean above and below zero. That's all they mean. Okay, they have nothing to do with direction or anything. So we know that on the right side it's above zero. We know on the left side it's above zero. On the right side it's below zero. So that means somewhere here potential has to be equal to zero. That's where it's equal to zero. But it's changing, right? It would be, -1 on one side and +1 on the other. Right? So saying V is zero isn't as significant as you might think, versus saying it's constant. Saying V is constant is a very significant, or potential is what I should be saying, not just V, is a very significant statement. Because as you can see, when it's constant, there's a very important thing going on. Okay. And so this is electrostatic equilibrium. That's really what he wants you to know about electrostatic equilibrium. But let me ask you this. Is there electric field outside of this charge? So there's no electric field inside. No electric field inside. But is there one on the outside? Good. Yes. Right? There's nothing to cancel this one out, or this one, or this one, or this one, right? There's nothing, right? Inside, remember, they're essentially, you could think they're butting heads, okay, and they're canceling themselves out, okay? But out here, this charge is just chilling by itself, right? It's just gonna have this, it's gonna do this, right? And what do we know? So there's an electric field out here. What can you tell me about potential then? Is it constant anymore? That's what I should have said that, sorry. It's changing now, right? It's changing now. Yeah, right? There's a change in potential out here. And look at, what do you know? Change in potential electric field. What do you know? What do you know? Right? But it shouldn't be a surprise, because it's like, well, that's because math told us already. We should kind of expect it. Okay, cool. Right? Like if this changes zero, then okay. You get super mathy there. I don't need to. All right. Okay, so that's I go over potential because I don't want you confused, because we do say it a lot of different ways, and sometimes it can sound like we're trying to say one thing versus the other, and we're not. Potential can be, trust me, I was literally talking to my mentor about 2 weeks ago about potential. We were just saying, like, yeah, man, especially when you understand the math side, like, it's kind of good you don't have to deal with that math side, because then it really makes it just like, but then it kind of clears it up too, I guess. So anyway, but potential energy, right? We were saying kind of like increases and decreases, and it works the same way here, right? We didn't write it, but when I'm closer to this charge, is the potential energy larger or smaller than if I'm further away? A negative charge, this negative charge. I bring it closer to this. Good. So it works the same way, right? And again, there's also a change. I didn't write it here, right? But there's also a change in potential out here. Right? So keep that in mind. And that's why, like with the battery, it's a lot easier because, with the battery and a circuit, yeah, I mean, we could talk about direction, positive X and negative X, but, as you can see, we don't use that as much. And so, when we talk about a circuit or something, it's better to use potential instead of electric field, because now when we talk about electric field, now that needs a direction, where in a circuit, we can just be worried about source and resistance and the current itself, and just the direction the current's flowing, to the right, in the system itself, uh, and not, be like positive X, positive Y, negative X, negative Y, positive Z, negative Z. And then, and because we're using potential, it allows us to do that, versus if we were trying to use electric field, we would be forced to kind of come up with some sort of directional scale for circuits as well. This means positive, right, and stuff like this. And you never heard that before, right? When we were in circuits, you never heard us talk about, up being positive, down being right. We never said those things, because when we're using potential, we're talking in terms of scalar values. And so we necessarily don't need to um, have some sort of directional scale, I guess. Anyway. Okay, and also keep in mind, I think he gives you some sort of picture, but like, he'll say, like, there's a positive charge here and there's a negative charge here and positive charge here. I don't know, he'll give you some sort of system, and then he'll tell you have some test charge, and you start to float it around here. Just think about what's going to happen. Like, if this is a positive test charge, as I start to bring that positive test charge closer to this positive charge here, is the potential energy going to increase or decrease? Imagine, like, I can hold this thing. It's not moving. Like, I'm bringing it close to the positive charge. Is the potential energy of that charge going to, well, let me ask you this. Is it, what's good? It's going to increase. And is it of the specific charge? Because it's the space between, right? That's really where the energy's at, right? Because as the potential energy for this charge increases, does the potential energy for this charge increase as well as the test charge gets closer? Absolutely it does, right? It's for both. It's not just this one charge is experiencing an increase in potential energy. Okay, both of them are, right? Because we know that sorry, it looks like a V. Has to do with these two charges, right? So you could think of it as gravitational potential energy, as well. Like, when you say your gravitational potential energy is increasing or decreasing relative to Earth, so's Earth's relative to you. And oh yeah, you've all talked about relativity now. You see where that's coming from now? I mean, it's in the equation, but right, like just because you move up, that's just like the Earth moving away from you, right? Now you know how we're thinking, right? You've got into the brain of us. Okay, so potential energy is going to increase as you get closer to this positive charge, and then as you start to move away from it, it's going to decrease just because of distance between those two charges, right? But what's going to happen as it gets closer and closer to this one? Like, when a positive charge gets close to a negative charge, the potential energy uh, decrease. Yeah. I mean, yes, it'll also like start to pull on it more and more as it gets closer, right? As it gets like, you felt this with magnets, right? Magnets, they could be sitting centimeters apart and not be attracted, but then you push them a nanometer closer to each other and they just suck together. that's you're feeling this idea of repulsion and attraction and how it works, because it's that's exponential. That's in terms of force, but this potential energy is still inversely proportional in some way. It's not inversely squared proportional, but it's still inversely proportional. Okay, so you understand this. I don't want to stick on this. I just wanted to make sure that you understand. Okay, as charges get closer, he might do something like this too. As charges get closer from each other, based off the charge, the potential you should have in your head, the potential energy is going to increase or decrease there. And if you need to solve for it, again, there's a lot of equations, to connect things. I think my pen keeps shutting off. For this situation, we shouldn't have erased it quite so fast. If you did have to do something mathematically, because that's describing it up there, but let's say like he, for these charges, he just gave like the potential, like everywhere here is going to be a different potential. And so you might also need to, because this equation would also be appropriate to use here, where you're looking at the change in potential relative to the change in potential energy per that charge, whatever that charge is. Right, so some change in potential between these two charges here, right? It's going to correlate to the change in potential energy for that charge. Another way to think about it. And it also works. And that's probably the more appropriate one, I guess, is what I should say for these situations if you need to solve for math. And again, in SI, we'll definitely work through examples, okay? Just trying to get through the concepts here. Okay. Any questions about, because I think potential energy is pretty straightforward, so I don't think we need to go any deeper in that. But any questions about potential, electric potential energy, electric force, electric field, anything there? Good. I think we've covered all those. There's one more thing we got to talk about, but talk about equal potential surfaces. Even if I didn't directly say it, because it looks like I didn't draw the picture, is that like for the equipotential surfaces, like this would be considered one equipotential surface, and there'd be another one. And so what is the results of something like this going on? Well, that means that if I like had a positive charge and I moved it along this line right here, since that's an equipotential surface, the potential isn't changing. That means that the potential energy isn't going to change. And that's that equation we actually just wrote. Is that it? No, I can't remember. It's times Q. What am I writing? So it's based off of this. So there's no change in potential, right? Because everywhere along this surface, it's the same potential. We call this an equipotential surface. So there's no change in potential. The potential is constant right there. And why? Because there's no what? There's an electric field. You might be confused here because you're like, well, there's an electric field there, but it's not in that direction. The electric field's pointing out. If there was an electric field also pointing in this direction as well, then there'd be a change in potential in that direction. But there's not. So since there's no electric field in that direction, there can't be any change in potential. That's another way to think about it. The potential is just going to remain constant because you got to have the potential can only change in the direction of the electric field. That's what this is essentially trying to show you. Okay, because there's a change in potential right here between the two surfaces. Between these two surfaces right here, there's a change in potential. But on the surface itself, if you were to move around the radius of the surface, there's no change in potential. Okay, so because there's no change in potential, there's not going to, what's the other significant thing you need to have in your head about that is that there's no change in potential energy then. Its potential energy isn't changing. Can anyone tell me what the significance of that is? That's a physics 1 concept I'm asking you right now. That's why I'm asking you. It's not physics 2. If we know the potential energy isn't changing anywhere on that surface, what does that mean? Then you don't have to do any work to move a charge around that radius right there. It doesn't require any work. And remember, work is just putting energy in or taking it out. So you don't have to, yeah, good, because that's what it's about. So that's the idea, right? Is that electric fields do work on charges. They do work on them. So if there's no electric field in that direction, there can't be any work done on that charge. And again, remember, what is work? Work is the transfer of energy. The transfer of what energy? Well, you can do work and transfer potential energy or transfer kinetic energy to it, right? That's what you learned about. And so if you were to move along that equipotential surface, there's no change in potential energy. So that means you don't have to do any work. You don't have to put any energy into that charge for it to move around this radius here. But if I wanted to move the charge from one equipotential surface to the next, I would have to do work. Why? First of all, the electric field's in that same direction. There's an electric field, right? It's everywhere. I couldn't draw every electric field line here, right? But it's clear it's in the same. If I were to move, or even if I were to move, it doesn't matter the direction, whether I move from the closer one to the further one or the further one to the closer one, I'm still moving in the direction of the electric field now. So because of that, I have to do work on the charge to move it from one equipotential surface to the other. And again, what does that mean when I say I have to do work on the charge? That means that I have to now put energy in or take energy out of it to move it from one equipotential surface to the other. Right? And one way the potential energy, decreases, it'll naturally move, and the other way it won't. Right? So the other one, I'm going to have to put energy in to it to move it back. But one way, and that's what this is telling us, right? It's going to naturally want to move from higher potential energy to lower potential energy based off the charge. But if I wanted to move it back in the opposite direction, I'd have to do work on it to do that, right? Because the electric field's doing work on that charge in the opposite direction. All right. So that's what we were trying to talk about with the whole work connection idea in this chapter. Does that make sense? Is everyone understanding what I'm saying right now? I'm trying to use some familiar language for you in terms of like work, and then letting you know, reminding you, because I think when we hear work, I think the first thing that comes into our minds is like going to work, because that's the first thing. Even myself, knowing physics, I think sometimes I still, right? Because we dread it, I guess. I don't know. But anyway, keep in mind that in physics, when you hear that word, all we're trying to say is transfer of energy. We could have said it that way, but we just came up with the shorter word. We said, well, let's just call that work. Okay. But it's transfer of energy. Okay. So no work along the equipotential surface. Why? Because there's no change in potential energy. Because there's no change in potential energy, there's not going to require any work. Or because the electric field is not in the direction, right? If it were also in the circular path, if it was also, oh my goodness gracious me, also in this direction, right? Then if there was another electric field in this direction, there was two electric fields, one going out and then one in the direction of the radius there, then we would have to do work there as well, right? There doesn't have to be just one electric field. Okay, this is turning into a disaster. Anyway, Cool. Is everyone good with that? I just want to make sure we understand equipotential surfaces and the idea of work and the amount of energy that goes into moving back and forth. I think we made it clear. That picture won't come back, and I'm not going to sit here and fuss with it because we don't need to worry about it. Everyone good? We're gonna move on. If you have questions, please ask them. This is totally for you. All right. What's flux? Like, tell me, and then we can get into the equations. So what's electric? Let's not just say what's flux. What's electric flux? Not quite. Like, electric flux, it was introduced to us actually in the electric field chapter, the first chapter we were introduced to this semester. Good. The number, so Levi's saying it there, it's the number of electric field lines in a specific area, right? That area has to be defined. Okay, like you know, let's say you have you know, just a bunch of electric field lines here. That doesn't mean you have, just because you have the electric field doesn't mean like, oh, there's flux. Okay, you have to define the area, and it doesn't have to be all. You could say, I just want to know the flux right here. Well, now that's your area. Okay, so, you know, it's not like flux is this physical thing, right, that you can see, right? But neither is potential, right? And neither, you know, I would compare potential more to like flux, right? Those two things are very similar in that way. It's like not something, you know, that you can see. We kind of just talk about it like it's there based off of some particular thing that's occurring. Okay, but we have to define that area. Okay, sometimes it can be defined for us. Sometimes the area is defined for us, right? But if it's not, like, there has to be some sort of area defined. You just because the point is, just because you have electric field lines doesn't mean you have flux. Just make sure that you have a defined area. Okay, good. Now, there's two ways to write the equation for flux. But they're both trying to tell you something very important. Okay, they both, you know, we're trying to explain I guess the idea of flux to you, but in two different ways. Like when we're taught this, you know, we're taught that this is like the math definition, and we're taught like this is the physics definition of flux. Okay, there's kind of two different ways to talk about it. So yeah, but that's not quite yet, right? So flux itself, right, has to be, right, I mean, the electric field isn't, you know, in terms of this chapter, what we're talking about, you know, is associated with some sort of, you know, charge, right? But, and that's what the bottom one's trying to describe, but the top one's saying like, hey, okay, but, you know, even if there's no charge there, just as long as you just have an electric field, you're gonna have flux essentially there. And again, this flux is electric flux. It's the amount of electric field lines in a particular defined area. Okay, so let's just make sure you have the few ideas that you know he he wants you to have in your head. Is flux a concept? I mean, a vector or a scalar? Good. And so where's its sign coming from? Good. Yeah, yeah. But it has to do like, what is this? This is a dot product, right? And this angle is the angle between electric force and area. Remember work was force times displacement cosine theta, and we would always have to get the angle between force and displacement. This is the same exact math. It's also a dot product. These are both dot products. Okay, so it works the same way. And what did this angle always give us in work? It always gave us the sign. This was always the sign, right? It was either positive or negative. Can't write. Right? And it works the same way here. This is going to give us the sign out here, positive or negative. Okay. And so is area a vector? Yeah, it can be defined as a vector, right? And it's measured in terms of what? The vector for area is measured in terms of what? The normal to the surface. So for the area over here, right? Normal's always pointed away from the surface, right? Never towards. Areas never looks like that. Like that's, or normal never looks like that, right? Normal's always pointed away. Like when we draw the normal force, it's always pointed away from the object, right? And so it works the same way. So here, right, like on the top, the normal is up, right? At the bottom, the normal is down. Over here, the normal is this way, right? But that's all that normal, keep in mind, is just the vector direction for area. Okay, that's how it's measured. So this is A and this is A for each side. Okay. Now, if I have, every situation is different, but let's say I have 3, coming in, 3 going out. Now, first, you should already know this answer, but if not, you should know how to calculate it and know how to get it. Like, do you know what the net flux is here? You should know. I think all of you know. There's a very conceptual way to say this. And that's really what you need to have in your head. It's 0, and how do we know it's 0? This is the concept. Remember, this is the thing that you want to memorize for flux, the thing we're about to say. Like, how do we know the net flux here is equal to 0? The same amount of what? Good. The same, and it's the same amount, right? Have the same amount of electric field lines going in one area and coming out the other side of this particular. You can imagine it's a cube or something like this. So that's one way to know, right? So if I have, again, that's the main concept, because you should be able to just recognize it right away. If I have, let's just do it on a different. I have 3 electric field lines coming in and 2 going out, you already know that there's what? Like conceptually already there must be what? Some sort of what? Good, change in flux, right? Automatically, the same amount of field lines that are going in aren't coming out, or vice versa. I mean, this could also, look like this too, like 3 going in, 4 coming out. Okay, but when they're not equal on both sides, automatically, there's some sort of net flux. All right, and what causes this situation? So this is very specific, right? Because when this is going on, there's something else. They're 2 different situations. I'm trying to say right now, but I think my brain's starting to but what causes, you should know this. He asked you a test question on it. That's why I'm asking you. When this happens, you know that there must be what here. I'm leaving that a little bit open, but I'll give you more detail if you need it. But I'm hoping you. So this is always caused because there's some charge on the inside. Okay. But if there's no charge on the inside, then the same amount going in is the same amount that's going to be coming out. But if there's some net charge, then that net charge is going to essentially cause a change in the electric field. And then because of that change in the electric field, there's not going to be the same amount coming in that's going out. Do you see what I'm saying? So if the charge is there, it's going to kind of like play with it. Yeah, that's another way. Again, like mathematically, that's another way to like for the specific area that you've defined, right? Like if the area that you've defined, if the electric field isn't constant, and that's what this equation is telling you up here, right? Because E has to be a certain value. If E is changing, if there's a change in E, oh my goodness gracious, then there has to be a delta flux. If area is changing, there has to be a delta flux. Or if angle is changing, there has to be a delta flux. Changing flux. Why do I keep saying that? Okay. Like that's how it works. That's like you can look at the equation, and it's the same thing with the other one, right? Like flux is equal to Q over epsilon naught. So here, right, this is a constant, so all you have is Q, but if there's a delta Q, then what do you know? Delta flux, change in flux. Does that make sense conceptually? How to think about that? Like I said, I'm doing this because there was a test question, and there's a couple. He asked you quite a bit about this actually. It's not just because of the test question. Are we good though with this? Okay, definitely wants you to know this. Okay, and mathematically, if you're wondering how this works, well then here, right? If we want to do the flux over here, it's going to be equal to E a cosine theta. But what is the cosine theta for this side over here? Area is pointed to the left, electric field's pointed to the right. What's the angle between them? Good. So what's cosine 180? So then this would be a negative flux, right? And then This is how you get the signs, right? And then on the other side here, what's the cosine? Good, this is 0, so that makes this positive. Now what you would do, right, is you would, this works for both situations, okay, even this situation. Okay, you would do flux over here, right? Get the you get the same thing. This would be negative, this would be positive, but what's different here? What's different here versus the other one? Why would this equation get us actually a net? Remember, we said there'd be a net flux here, right? Why would mathematically we'd get a net flux here and we wouldn't here? Either way, we're going to essentially put them together and say, like, if we call this like flux 1 and flux 2, it'd be, flux, just to make sure this doesn't look weird, I'll just write it in this order. Right, and this would be net. That's the equation for either one, right? For either one. So right here would be oh. Sorry, that's what I meant. For this down here. So what about the math? How do we know mathematically this would equal 0? And this one would equal some number. What's different about them? Look at the picture. Remember, this is for this side. This is for this side. Just like over here, this was for this side. This was for this side. So this goes back to the very first thing we talked about, and then we're going to move into circuits here, okay? But the very first thing we talked about today, which was, and again, it's interesting, and take this to note. Just know, just make sure that you refresh a little bit, because I think all of you have it, okay? Don't take this as like, man, I thought I understood this. No, you do. Just make sure, where things always get challenging is when we have to apply it, right? So is the electric field the same on the right as it is to like over here, as it is over here? Yeah. How do you know that? How do you know? Just by the picture, you should be able to recognize that. How do you know that? No. How do you know the electric field isn't the same? Yes. Because remember, that goes back to the first thing we talked. Like I said, applying it is challenging. Like, we'll talk about it all day. Pay attention to the electric field lines. If there's more, if they're closer together, if they're moving away from each other, all that stuff means something. Remember, we said that? More there, less there. Yeah, when we're saying it individually, it's like, oh, no, I understand. It sounds very simple. And I think that's where a lot of this stuff with electric field and magnetic field get tricky, because when we're telling you these things like that, like, look at the direction of electric field, when we're first talking about it and teaching it to you, it sounds so easy. It's like, yeah, I got that. But it's like, look what happens when you have to apply it. It's like, oh, crap. I thought I did get that. I thought I understood that. I thought I'd be able to recognize that everywhere. But I like right here, simply, I see 3 electric field lines on one side, 2 on the other, and my brain doesn't register that as this, doesn't say, hey, wait a minute, that can't be the same electric field. There's not the same amount of electric field lines. That's a direct indication. You see what I'm saying? It's a concept thing, right? Versus over here, there's 3 electric field lines on the one side, 3 electric field on the other. They stay the same distance apart and everything, right? Same electric field on both sides. You don't need any numbers. You see what I'm saying? You see what, and this is what Dr. Dungano wants you to do. This is why it's so tricky. Why he's tricky. Like, you don't need math. You don't need the math. Just the concept. And trust me, we have said, I'll tell you this right now. This is something that if you talk to any physics professor, they would probably say. So take solace in this, is that more often than not, the algebra students who walk out of physics 2 actually have a better understanding of physics than the majors, because they don't get into these concepts. It's just a math. And then they don't learn these concepts, but these concepts are the physics, right? So you all are walking out of here actually understanding. You have like these concepts in your head. You may not be able to do all these derivatives, but you understand the physics. Isn't that more important, right? So take solace in that. It's actually a great thing, but we test you on these concepts, okay? And the concepts and the math, they blend so well together. All right. Is everyone cool here with flux? Because I know that was a tricky thing. This versus this, and right. So here the electric fields aren't the same. So these numbers wouldn't be the same. That's what I'm trying to say. If this electric field over here, because it's smaller than this one over here, which is larger, this is large, this is small. When I do the math up here, there's going to be some number left over versus over here, right? This is they're the same. The electric field is the same number. The area is the same number. The angle is the same number. Or I mean, sorry, the angle is not the same number. The angle is just given as positive or negative. Sorry about that. So this is going to be equal to 0 up here when we do the math. Okay. Good. Any questions? We're going to move into circuits now. Okay. And circuits are, it's really, again, because he wants you to understand the concepts of things, is why circuits can be, they can be kind of challenging, but the math of it, I think, is pretty straightforward for circuits, right? I mean, but let's make sure that we have the concepts for them. So I'm trying. They only give me a certain amount of slides here, so I gotta kind of recycle. All right. Okay. So circuits, current, all this stuff. All right. First of all, this whole idea is based off of some source that has some sort of charge, right? That's connected to some sort of wire, right? And that wire, if we don't have a resistor in that wire or anything, it's kind of pointless. But that wire essentially takes the charge from the source and supplies it to the resistor or the capacitor or the inductor that's in the system. And then the resistor, capacitor, or inductor, they do something with that charge, right? That's essentially what circuits are, what current what we're trying to explain here with the general idea, I guess, is what I'm trying to say. So I think, current's pretty straightforward. Current, is what do you, believe it or not, it's kind of, he may, but it is important to make sure you do have that idea in your head. And it's not Ohm's law, even though that's what we need to talk about. Do you know the equation for current alone? Like, current has like its own equation, like separate from Ohm's law. Do you know what it is? Like, what is current, essentially, is what I'm asking you. And it doesn't, you don't have to tell me mathy. It's just the equation really is it kind of covers everything at once. But you can just tell me what charge is if you want to. I mean, not charge, current. You're really close. Yeah, it's just the amount of charge per time, right? Good job, Sheila. Yeah. Right. So when you think about current, like every time we use that word current, you know, that's all we're really trying to say. All right. If I have one charge that's moving, from the left to the right, is that current? Is that considered current? Yeah, because it's just moving. It's just how the charge is moving per time. That's really all current is, right? Like, I think most of your biology majors in here, and those of you who aren't, I'm sorry, I'm just trying to, but I think all of you have this idea in your head. You don't have to be a biology major. Is your the when you have an action potential in your brain, the sodium moves in one direction and the potassium moves not at the same time, right? But moves in one direction, moves in the other. Is when the sodium is moving in one direction, is that considered a current? Good. When the potassium is moving in the other direction, is that considered a current? It is, right? Either one. Potassium moving in one. They don't do it at the same time. And again, I think he was asking you questions about net, right? If there's a net current, because you can look at that based off, so look at those. He asked you a lot of questions, I think, about, or not a lot, but he asked you some conceptual questions about current, but I think it was about net charge and stuff like this, right? Because if there's no net charge, you can't have, essentially there's no current, because current requires charge. Even though there's moving charge, if there's no net charge, there's no current. And he went through some examples like that, but we're not going to focus on that too much. I just want to, that's where we started. Okay, cool. So that's current. Current is just moving charge. What is it about the battery that allows the current to move? So when we hook just a basic, what is it about the battery that allows the current to move through the system? So it has a change in potential. That's true. But what is it about that change in potential? Just because you say the battery has a change in potential, what does that mean about the current moving through the system? So think EMF. What do we mean now? Because we call potential, right? When we talk about Ohm's law, we write it two different ways, right? We can write it this, or we can write it like this, right? Two different ways. But these two things are describing the same thing, right? difference in potential doesn't create a force. And it's not, don't, it's not really bad. So the battery does work on the charge, right? The battery increases and decreases the potential energy of the charges, right? And then when the charge has a high potential energy, it's going to, move through the system, right? It's a high, U is high. It'll move through the system, and it's gonna, when it gets over here, it's not gonna have any more potential energy, electric potential energy, right? That the battery gave the charge because it used it all where? Right here. What do we know happens at that resistor? It causes a change in voltage, and how? What is that resistor doing? Good, Sheila. You're thinking good. It does work on the charge, right? And what does it do to the charge? Does it increase or decrease its potential energy? Remember, this isn't something we talked about before, how changes in potential equal changes in potential energy. Really doesn't matter to the system. Oops. So it decreases right. It doesn't have, it does work on it. So essentially the charge has to fight its way through this spot right here. That's why there's a change in potential right here. Right? And if its potential energy is decreasing, then what does that mean? You can look at the potential equation. What does that mean its potential is doing? Good. Decreasing. Right? And that's exactly what we say, right? When we look at these circuits, this is the stuff he wanted you to know here at the beginning. Very important that we know, because the series and parallel stuff is, I'm not saying it's easy. Please don't misunderstand me. I'm just saying it's straightforward. What we want you to right. I mean, it's very clear by the pictures. Series or parallel. We have one way to put it together this way, one way to put it together this way, right? But the concepts behind this are like, right, and they're actually more applied. I think you use them more for like Kirchhoff's law and stuff like that. Is this idea of like the potential being high on one side, right, and the potential being low on the other. But keep in mind when we say that, we're talking about like the potential energy per charge, right? So when the potential decrease, right, when we say the potential is lower, what do we mean? What does that mean when we say that? Well, that means that the potential energy is decreased per charge on one side of that versus the other. And then vice versa, right? If I were to move this way, right, then we could, so if I move, sorry, I made a jump there, but didn't say the first thing. So if I'm moving this way through the circuit, right, I can see that I'm going from a high potential to a low potential as I move through the resistor, right? But if I were to go the other way, then I'm obviously moving from a low potential to a high potential, right? So it just depends um, which way you're moving through the resistor based off, again, the way the source is set up, right? We have the potential's higher over here because the positive end of the battery's on this side, and the negative end of the battery's over here. So we know this means high potential. V is high over here. We know over here V is low. Again, not from this picture. Where did we learn this? Here. V is high, V is low, V is high, V. It doesn't matter the charge, right? And then that's how you apply them to a circuit. You put them in the circuit, so we can see, right, that when we move, if this current is maintained, then as the current moves through the battery, it's moving from a what? Low potential to what? High potential, right? Kind of the opposite than what it did when it moved through the resistor. And what is that? What does it mean when it goes from a low potential to a high potential in the battery? That means that the battery is doing work. It's increasing the potential energy of those charges. And why is that important? Because that's what that's what a battery does. How does the batteries apply or supply energy to my device? The battery gives the charge potential energy. How much? Based off the voltage of the battery, right? And then it sends those charges through my system with the amount of potential energy it's given, those charges, right? And then the charges lose that potential energy as they move their way through resistors, but they could also regain some potential energy, right, from a capacitor or from an inductor, right? Because those can, we know capacitors and inductors can increase our potential energy, right? Decrease, like that, they do, you can do that as well. So that's the idea. But does this make sense? Because remember, he had you do all those things about like move through the battery this way, like, right? Like one of his worksheets, he was like, this was point A and B and C and D, right? And then he had you, he said like, is the potential increasing or decreasing between point A and B and B and C? And then I don't know if you remember, but I know I do, that in your first test, like he asked, this is where a lot of the questions were asked, right? Is about like moving through the circuit, just making sure you understand the change in potential, how it's occurring, increasing, based off the way that you're moving, right? But current, right? When we talk about current, because and that was the other takeaway from here, is that for any type of circuit like this, that we assume, even though we know it's the electrons moving, for all this stuff, when we talk about current, so we'll either ask you about the movement of the electrons or the movement of current. If in a circuit, well, the current's always going to be from positive to negative, even though we know the electrons are actually moving this way, and they're the ones actually supplying the current. Like I said, we're not, since none of this is really vectors, we're less, we know the same thing happens for a negative charge, just in the opposite direction. So nothing, it's like nothing new to do. It's not like we need to do new concepts. Look at that situation as well. We just know that the opposite's occurring. Why they've never changed the way they teach it, I don't know. But anyway, I guess because physics is hard enough. Anyway, all right, everyone good with the ideas of a circuit here? I don't think, and I think sorry, just I forgot you. I mean, I mentioned them, but just keep in mind, we got these Ohm's laws over here. But the one thing I forgot to do is kind of, not that you don't know this already, you can test it on it, but these equations that we wrote over here are they're appropriate for some situations and not for others, right? So this one is more appropriate for the source, right? We're typically always writing the source as E equals I times R times, right? And anytime we're talking about any change in potential, right? Whether it's through a resistor or whether we're talking about the change in potential related to a capacitor, right, or an inductor, we use this type of, this is the, let me do it in a different color. This is the appropriate equation to use for those situations, right? Does everyone understands that, right? Like, even though we write these different, they mean something a little bit, different. Like, we're trying to specifically say every time we use this E, we're specifically always trying to talk about the source. And anytime we're trying to use this delta V, we're trying to talk about the change of potential, like, within the system. Make sense? Okay. So again, I think you know that, but just keep that in mind, because that's a thing that we use, um, uh, uh, for any type of circuit, right? Even when we're in the RLC circuits. Oh, and by the way, geez, I forgot to mention the most important part, I think, probably about this chapter. But it's simple. It's just, this is all DC current, right? Where now that we've talked about the two different types of current, it's very appropriate. We need to say that. We need to say, okay, these circuits right now, we're talking about, like, the way we're drawing the source. It's not how we draw an AC source. DC sources only have one direction of current, so it's just going to work this way, right? If it was an AC source, I would have to, have current both ways, because it's, an AC source is fluctuating both ways, right? But we also know that the source itself works a little bit different. It's just not like this battery with just the potential, right? We know it's some sort of a generator type source, right? So this is, this is DC circuits. Is the way to make sure that you're distinguishing this from, like, it's like, well, what about those circuits we talked about after magnetism? Yeah, the difference between what we're saying now and what we're saying over there is the difference between DC circuits and AC circuits. That's the difference. Okay. But hopefully you notice some things, right? Like when we were talking, because the RLC circuits, when we were talking about those, the chapter is very specifically labeled series. And that means something, right? And it didn't mean anything different than it did in this chapter, right? Versus, like, parallel, right? So, keep that in mind. And with that theme, let's talk about it. Like I said, I gotta kind of recycle things here. I think I got a few extra slides. So what is this whole series parallel? I can't even spell anymore. My brain's going away. Good thing the next, I got another review after you, and it's Physics 1, and it's just like Newton laws. So my brain doesn't have to be so on. Okay, so what's the difference between these? Apparently, my writing's going as well. What is the difference between series and parallel resistors? Because he didn't get into the series, even though we could have, and I think they're in the chapter. I think we just skipped them. But, like, series and parallel capacitors is also something we could have brought up as well. But I don't think he did that. I think he just stuck with the series, the series and parallel resistors. So that's what this is specific to. So series is when they're, in line with each other, right? Or parallel, they're connected. And this is what's important for you to know. This is the verbiage that you should have in your head, is that for parallel, they're connected by what we say a junction. Okay, and the reason why you want to know that is because that's how you identify it. That's how you identify the difference, right? Because, I could have a system that, here's a resistor and here's a resistor, right? And then here's a resistor, like this. And it's like, oh, well, these two things are opposite of each other, so they must be parallel. No, that's not the criteria for parallel, is being opposite of each other. The criteria for parallel is that they are connected by some sort of junction where the series aren't, right? Here, it's just the wires just bent. There's no junction, right? There's no like there would have to be some sort of split. And then right there, now these are parallel. Why? Because the junction, right? This junction right here. And as you can see, that junction verbiage we were talking about, but that's very important, especially when we get into Kirchhoff laws and stuff like that, right? Is that, this junction it's an important word to have in your head. Why? Because first of all, it separates the idea between like what's a series and what's a parallel resistor, right? Or anything in a circuit. Capacitor could be capacitors, right? Capacitors, if they're parallel to each other, if they're separated by a junction, it means the same thing. Okay, so series parallel, that this idea stands, whether it's a resistor, inductor, capacitor, all these things, right? And we saw in the RLC circuits, everything was in series. So that was a good thing, because when everything was in series, we were able to use all the properties of the series, or all the concepts that we understand from the series circuits versus the parallel. Now, so what are those? What are those concepts? What do we know about potential and current up here versus potential and current down here? Good, exactly. Sorry, I don't know if you guys can hear, there's a dog next to me. I think I told you all, I share a yard with Dr. A. She's the anatomy professor at CU Denver. She's like family. She's my family. Anyway, her dogs just come and visit me. I leave the door open for them, actually. They visit me so much, and I have stuff. Anyway, one just walked in. He's making all kinds of noise. I hope it's not bothering me. All right. But good. Potential is changes. I don't know what that equal sign is for. Potential changes, current stays the same. And what does that mean? It's more apparent for the parallel, right? But we know that everywhere we already talked about this, right? Everywhere there's if current was moving through here, everywhere that there's a resistor, there's going to be a change in potential at every point at every point that there's a resistor. But the current doesn't change, right? The amount of current. So when there's a change in potential, charge doesn't disappear. The only time charge disappears if something is severely wrong, like you have your system. There's something you should not be losing any charge if you have an electrical system. That's how things catch fire and stuff like this, and all those things. So if in terms of series, the amount of current entering over here, no matter how many resistors it goes through, is going to be equal to the amount of current moving, coming out the other end. What has changed, though, about the current? What has changed? Something's happened to the current. We didn't lose charge, though. The amount of charge per time is still the same. But what did change about the current as it moved through those resistors? Talked about it over here. Well, we talked about it a lot, but don't we talked about it over here. The U's. What happens? There's a change in potential, but when there's a change in potential, what does that mean is happening to the current as it moves through the resistor? It's having a change in potential energy. Okay, good. So that's what's changing. Okay, but the charge, like the amount of charge per time it's flowing, the reason why it's the same is because it's hooked up to the battery, it's just pushing it through, right? So Just think of like, you know, I don't know what analogy. Anyway, yes, we understand. Good. So that's the idea. Okay, so charge isn't changing, and charge is the Q per T, and that didn't change. So yes, so that's what we know. What about for parallel? In term, what do we know about potential and current in terms of parallel resistors? Good. So current changes, right? But potential stays the same. What does that mean? Yeah, same. Sorry, it's the best way to say it. What does that mean when we say the current changes, the potential stays the same? I thought they're moving through resistors. What the heck? And I probably should be writing change in potential, by the way, as well. I'm just writing potential, but the potential does change, but it's, you know, the change in potential. Right? Either way. But it's probably more appropriate to say that. Good. Yes. How well? It's the same for what? You got to go a little bit farther with that, Levi. Not the way I was wanting you to go. You already said each resistor, actually. You already said this change in potential for each resistor is the same based off the amount of, this is for everyone, the amount of what going through that resistor. Yeah, think you remember the change in potential, it's only happening because the current, right? So when we say the potential change is the same, that means that the change of potential that the current experience, the amount of current that's going through that top one is going to be the same change in potential that the bottom one's going through. They're going to be equal. Okay, it's the same amount. How is that possible? How in the heck can the change in potential up here and the change in potential be up down here be the same for the current that's running through it? The amount of current that's running through that specific resistor. Sorry, I should have said it in that detail. Not quite. You do need to know this. This is important. It has to do with the other concept for parallel circuits or parallel, right? Has to do with that current side. The reason why the change in potential is the same, it has something to do with what the current's doing at that junction. Hint, hint. Okay. And how does the current split? What the junction causes it to split, but you should know literally value wise how it splits. You should know. You should have a conceptual idea how the current literally splits here. Think of well, everything does this. This is the reason why No. It has everything to no. It has everything to do with like why lightning looks the way it does. Why that might not have been a good conceptual example for you. Why oh, this one will help you. Why a river flows the way it does. Does that help? Water always flows in the path of least. Yeah. And that's how, so one thing we didn't talk about so much in here, but it actually probably would help you with the concept because he does want you to know this concept, is that resistivity is directly connected with something else we call conductivity. Okay. So the higher the more resistance, the less conductive that resistor is going to be. Does that make sense? So essentially, the more resistance resistor has, the less current it's going to attract. And so if the current, again, as you've seen, it's like everything's thinking, right? When we think about these light particles, everything we've talked about this semester, that's why us physicists say that. We literally talk about these particles as thinking, because it's like, what the heck else could be going on? It's like they're thinking. It's like these particles are going through the circuit. They're like, oh man, they can like look ahead and say, you know what? That's going to be way harder to go that way. But some of the friends are like, I like the harder way. So some of them go that way, right? But most of everyone else is like, man, this way is so much easier. And so they just go through the smaller resistor, right? So the charges going through the resistor with more resistance, they're going to experience a larger drop in potential, right, than the ones going through the smaller one. But there's going to be more charge going through the smaller one, right, than the larger one. So when they come back together, the total potential of them was the same as if they just had the same potential drop, or the potential drop was the same in both resistors. You see how that works? Isn't that cool? It's like crazy how it can how all this stuff can think, right? It's like it's thinking and it's mind-blowing. Anyway, you'll probably really think, I get a lot of students, they'll like write me, next to me, after they're out of physics too for a few months, and they're like, Carl, I actually started thinking about all the stuff we were learning about. Now my mind's really blowing. So when you get a chance to think about it, you'll be like, whoa, was that really what we were saying? It's like, yep, that's really what we were saying. Okay, so how do we do the math here? So if I needed to combine two series resistors, right? So this is R here, this is R, like R1 and R2, versus here, this is R1 and R2. How do I combine the series ones? Like mathematically, very simply, I just directly what? Just add them, right? It's just R1 plus R2. We don't have to do the inverse of them, right? And this is going to be equal to, we call it R equivalent, but that you can call it R net, but we don't use those words. We use REQ, but it's just the equivalent resistance of the two put together, or the 3 or the 9, right? I mean, this can just, if you have 20 resistors and they're all in series, it's just R1 through R20 that you add up, right? It doesn't get any more complicated just because there's a lot more resistors. All right. And then what about for parallel? Well, it's just the inverse, right? So essentially it's 1. And again, this mathematically is trying to describe what I just described to you, but we look at them as instead of directly, we can look at them in terms of a fraction, because the way that the current's splitting, it's not splitting exact. When would the current split exact? Let me ask you that conceptual question. When would the current like when there's a split, when there's a junction, when would the current split? What would cause the current to actually exactly? So if they have the same resistance, the two resistors, then the current will split perfectly. So that's a concept you can keep, like sometimes we try to make questions tricky by maybe throwing a couple of resistors at there, but sometimes you can really look what's going on. You can kind of get some hints, right? But that's a big one, right? Current's going to split equally in those situations. I don't know what the significance of that could be, but good to know. Okay, good here. Again, if we want to solve problems, that's what we're going to use the rest of that. We have there's quite a few to SIs left, like 4 or 5, and I might even do an extra one for you on Monday, a question, like the Monday before your final, like a question and answer one where you can just come in and ask questions, whatever you want. But and that's how all the SIs will work too. But I'll give you an extra one in there. So please, if you want to work through this stuff mathematically, I have no problem doing that for you. It's just, it was either go through the concepts or go through the math. But who knows the math? He could ask you so much different math. And then also, as I said before, because we're coming, there's 15 minutes left, and all we got to talk about is Kirchhoff laws. But know that if this records and works the way it's supposed to, then I'll send out because I already did a review for this stuff, right? That video is still up on YouTube. I'll send both links together so that you can refer back to that one, because on that one I think I did the worksheets for you on that one, didn't I? I think that first one, that's what I did, because there were so many worksheets. No other section had that amount of worksheets, right? The next two sections, only certain sections had worksheets, so we couldn't do the other reviews like that. But that first one was pure, right? Pure. So that's what we did there. So please refer to that if you need to see those answers, because we did work through a lot of problems on that review. If you need to see worked out problems. And then also keep in mind, again, I know some students from class that didn't make it today are going to be watching this review, but please keep in mind, you can send me emails and ask me questions too. Don't, and same with Dr. Dungana. Don't wait until, or just don't hold anything in, okay? I promise you, him nor I will hide anything from you. We're just going to give you answers now. All right? But you need to talk to us and tell us what you need, okay? Because we got your back like 2,000%. Everyone in this class, okay? And we're so proud of all of you, by the way. You've done an extremely amazing thing in a very amazing time. This time has been very difficult to go to school in, and that says a lot about your all resilience and stuff, but that's a different conversation. But do know we have noticed that. Dr. Nungana has brought it up to me a few times, and we're very proud of all of you. It's amazing, amazing. Okay, so for Kirchhoff rules, and these are really easy, it's going to take a second to do, and you already know how to do them anyway. But they just had, they have defined rules, just like we just went through the defined rules for a series in parallel resistors. So essentially, right, Kirchhoff rules defined, and my brain almost gone. Not that I could spell this person's name well anyway, but it's something like this. I hate. I don't want to be disrespectful to these scientists, but I believe that's it. And so it was based off two things: the junction rule and the loop rule. Okay, so and each one, right, was defined in terms. So the junction rule was trying to talk. We've already kind of talked about it. Junction rules directly related to current, right? These junctions for parallel, right? What was the, when I'm gonna lose my words now here, but the junctions created a change in the current. So anytime you hear this junction rule idea, you should think, oh man, that has to be directly related to current, because junctions affect the current. How can a junction change the potential? right? It can't. It won't. Junctions only affect the amount of current that's going to then, right? Junctions always split the current, where the potential is being affected where? At the battery and at the resistors, right? And these systems are a little, right, like before we had like, resistors in parallel and, resistors in or parallel and in series. I'm saying that backwards as I draw these, right? But these systems for Kirchhoff, so if you have something very simple like this, you just want to use the parallel series thing. But Kirchhoff rules are become very important to use. You can't use that. In fact, you can't even use that other stuff when you have like multiple sources, stuff like this, or like you have multiple sources and then like a unknown current as well, right? Because you're going to have current coming from both ways here and stuff like this. So it's these types of systems that you want to think Kirchhoff. These types of systems you want to think just series parallel idea. Don't try to Kirchhoff's. They will work, by the way, but that's a very, very complicated way to try to just take care of a couple resistors that are in series or parallel, versus where you have two, where there's just one source, versus where you have these two sources, these resistors that are in series and parallel. Like it gets very tricky at that point. So you need a better tool, and that's what the Kirchhoff stuff's doing. It's the better tool. Always works, where the series and parallel stuff just works some of the time. And so I mean, there's a lot of ways to write this, right? But you could say I1 plus I2 is equal to I3, right? That's one, and essentially trying to move fast now, and then I'm flustered. So right, like this would be just an example. It doesn't always have to be, right? But like we could say like this is I1, right? And this is I2, and then this right here is going to be I3. And so they combine, right? I1 plus I2 gives us I3, right? There's a there's a lot of ways as you've seen, you get to choose the current. If he gives you the current direction, he's make sure that you make some sort of valid equation that makes it. Sometimes, I guess what I'm trying to say is, because all these different scenarios are going through my head right now, what I'm trying to say is like sometimes you might like looking right here might not be I don't want this picture to be deceiving, I guess is what I'm saying. Like this might not be the best place to look to make the equation. Like the way I drew these currents, so like it's like, yeah, look right here, they're equal to that equation I was just saying, right? But if he's given you the currents and you got to come up with that equation, like if you look at a spot and you're like, I cannot figure out if I need to add I1, or I can't see what I got to do there, go to the other end and say, okay, it's maybe this other end's less, even though yeah it's where it's splitting, but your brain might process it better, because the equation that you get up here and the equation you get down here, they're going to mean the same exact thing. Okay, so keep that in mind, and then mathematically, once you have to deal with that, this is the thing you want to use. I mean, you can also make this equal to 0 if you wanted to, but I don't know, right? Because these two, right, combine to make I3. So that means if I were to add them and then subtract from I3, that's going to give me 0, right? So there's two ways to write it, but putting it in the system and writing verbs for the system. And by the one way, you'll only have one of these, right? Where for the loop rule, you're going to write an equation based off the amount of loops you've established. So when you're doing this Kirchhoff law, I'm just going to draw the circuit again on this page. I can't keep going back and forth here. That's going to waste a lot of time. So with Kirchhoff law, right? I think like was curving my, why it keeps doing that, but, so you're going to have, one type of, current going through here. You shouldn't have two equations for current. Okay, just build one, and you can either build it off of writing it based off that junction or this junction. That's what I was trying to say. But the loop rule, right? You have two loops, and you could have more if there was more squares here, but we don't give you any more. And you can establish these loops, okay? Like, and one thing I like to do is kind of label up these points, because when you label up these points, they kind of label, if you call this point A, point B, point C, point D, point E, point F, right? They kind of help you establish your loops, but they definitely help me explain it to you. So that's where this is going to be helpful. So, right, I can make a loop that is from A, B, E, F, or I could make a loop that's what? That goes from A, that goes from A, B, C, D, F, right? That can also be one loop. Like, it's up to you. Like, there's no rules on the loop. You just make the loop. Okay, but the way that bigger one that I made is kind of dangerous, because now I'm going to have these two in that equation, right? So there's logic behind the decision. It's like, man, that loop from A, C, D, F, that's going to have these two sources in it, and especially there's you could potentially end up with two unknowns in one equation. That's not what you want. You want one unknown per equation. Every equation should essentially have one unknown per equation, and then you're able to just put everybody together, right, in some sort of fashion. You'll have three unknowns, but you'll also have three equations. So three unknowns, three equations, they let you solve for everything, right? So you want to make these loops, make them smart, make sure that when you make them, right, typically when I try to make my loops, I try to just put one source, and this thing is going to drive me bonkers. One source per loop is how I like to make that decision, and I think that's kind of a rule of thumb, actually. But it really is based off your question. Okay, I'm digressing too far. I think we all understand this loop idea. Okay, but the idea is that when you set up these loops, right, you're going to have this total change in potential that's going to be equal to zero. Okay, so the sum of the changes in potential. So you'll have a change in potential at the battery, and you have these changes in potentials at the resistors, right? So as you go to make, and now I got to move to show you how to do this, but we're almost done. I know we got 3 minutes left. So this is where now that thing that we talked about at the beginning with circuits, of knowing, like, going from high to low, low to high, kind of comes into play. So if I have a resistor, and let's say that this is the way it's set up, so we know that current is flowing this way. Okay, that means that this is going to be low, this is going to be high, this is going to be high, this is going to be low in terms of potential, right? In terms of potential. Okay. So these are the things we have to look at, because when you make your loop, right, your loop might not necessarily be in the direction of current, right? If I establish my loop, to go this way, and then I want to build that change in potential equation for the loop rule. Well, let's throw two resistors in here, just so it'll look like what you're used to seeing. So that's my loop, but remember, we know the current is going in the opposite. Current is going that way, but loop is going in the opposite direction of current. So as we write this equation, we write the equation following the loop direction. but keeping in mind that the way the current is flowing is dictating, you know, high potential to low potential. Okay, so essentially, and you can start anywhere you want to, right? But we have a change in potential here, a change in potential here, and then this change in potential is EMF. So if we're following this loop rule, as we move through this resistor right here, this is also high, this is low. As we move through that resistor right there, moving from high to low, also following the loop is also moving that way. Is our change in potential going to be positive or negative? If we're following to the, we know the current, I got the current is in the black color and the loop is in the red for that resistor. We're moving from a high, whoa, we're moving from a high potential to a low. Good, good. Remember, this is all mathematical. There's no physics really here. So it's final minus initial, right? Well, the initial is high, so it's large. So you could essentially say, okay, well, it's going to be some large number minus the final is going to be low, so it's going to be small, right? The small number minus a large number is going to be negative, right? It's like 1 minus 5. If this was 1 and this was 5, it's going to give you a negative number, right? So that's how we know the change in potential is negative there, right? And what about for the second resistor? The change in potential is going to be what? What's the sign here? Good. Positive again. Oh, I'm sorry. Is it going to be? Hang on. Did I read that right? No, it should be negative, right? Oh, I wrote. Sorry. I'm so sorry. I just really messed up. I'm so sorry. You're right. Based off how I wrote that. Sorry, I noticed the time when I started. I shouldn't do that because I didn't need to move fast. I wrote those backwards. I am so sorry. You guys should have caught me on that, but that's okay. It's not your fault. just like, Carl, based off the way the current's going, this needs to be high and this needs to be low. That was my fault. They can't go. I already said which way it was going. That was my bad. So yes. So based off what we're going from low to high over here. So this would be positive. I apologize. This would be, in this case, right? The initial would be low, small, and the final would be large. So that's going to give us a positive number. I explained it backwards the other way. So that's going to be positive here because we're going from low to high in terms of the loop, even though the current's going in the opposite way. I so apologize about that, but thank you, Jordan, because you answering allowed me to see that, and I appreciate you doing that. So here we go. Okay, good. Then positive potential up here, right? That's going to be the change of potential is going to be positive again, because even though the current's moving from low to high, the loop is moving from the current's moving from high to low. The loop is moving from low to high, right? And then when we get to the battery, what's going to be the sign for the E there? We're going to be moving this, this way through the battery. So don't worry about the current for the battery. Just look at the high and low and look at the direction we're moving through there. Yeah, so we're going, the initial is going to be high, the final is going to be low. So that means this E is going to be negative. And now now that you have the signs, you can just write this equation, right? And we can call this V1 and V2. So we can say, okay, the change in potential 1, right, plus the change in potential for V2 minus, we're just using the signs that we got, the EMF, right? And then that's going to be equal to 0. And then here, right, you could represent, these as I times R if you need to. Sometimes you need to make that exchange. So know that you can do that. Okay. And then just one more. I just want to make sure you can do this other one. right? So what if it's the other way? The way we just did is the complicated one. The second one is really, really simple. It's actually the easier one, but I always like to start with a complicated example. But let's say that we have, you know, the circuit again. Now these are backwards. So now the current's moving this way, and our loop is also going to be in the same direction as our current. So now our current is moving from high to low instead of low to high. So make sure it's an accurate picture. This should be a positive side and a negative. So this is going to be high. Low. Again, these low and highs are all in terms of potential, right? So we have a delta V that's going to be at that resistor, a delta V that's going to be at that resistor. We want to know if those are going to be positive or negative, equal sign positive or negative. And then we have an E here. So let's apply this loop rule one more time. Okay, so we know here, based off this loop, delta V is going to be equal to 0. Okay. Now let's start with the first resistor. What's going to be the change in potential, the sign for the change in potential for V1? Again, the current and loop are in the same direction now. Before they were in opposite direction. Now they're in the same direction. So when we go from high to low, that's gonna give us the negative sign, right? So if we have a change in potential, and our final is or small, what we can say small, and our initial is large, which is what we have right here. We're going from high to low, and then again from high to low, high to low, high to low. So that means we're going from large to small, initial high, final low, initial large, and final small. That means that the change in potential is going to be negative there. And then for V2, because we're also going from high to low again, it's also going to be negative. But through the battery, since we're going from negative to positive, where essentially the initial is now going to be small and the final is going to be high, that's going to make this positive. So now to write the equation, we can just put all these together now. So it would be the EMF we'll start with because it's positive, and minus delta V1 minus delta V2, that's equal to 0. And then again, if you wanted to, you can make these equal to IR. All right, 7 minutes over. Sorry about that extra time. But I wanted to make sure, because that one's a little bit, there can be two different scenarios. So I didn't want to, I didn't want you to think there was just one. You kind of got to see both. But again, if you want to solve problems with this, let me know. Those are the concept. So, all right. So that's section 1 here. On Sunday, we'll be, going through section 2, which is the magnetic fields, forces and stuff like that. But if you have any questions, ask away. Otherwise, thank you so much. You guys, everyone did a fantastic job. I'm proud of all of you. So for several reasons. But yep, have a good one. See ya. You're so welcome. Bye. See ya.